Now we come towards the period of revolution, and when we will analyze period of revolution, we will come to know that the satellite also obeys the Kepler's third law. That is, the satellite is moving in an elliptical orbit or a circular orbit around the another body. So the time taken by satellite for completing one revolution of Earth is called the period of revolution of satellite. That is called the time period of revolution. So period of revolution of satellite is given as 2 pi r over v, where v is the orbital velocity, r is the distance of satellite from the center of mass of the another body. So it will be 2 pi r over v. But if r is, that is, if r means if the satellite is at height h from the circumference, then r must be taken as re plus h. Then time period will become 2 pi into re plus h divided by v. That will be the time period. So where time t is the time period of satellite at height h. Now time period is given by following compositions: 2 pi under root r cube over gme. We find here that r is variable, but g, m, e are constant. G is the gravitational constant and m is the mass of the Earth. So, when we will write equality, 2 pi is kept as it is, and r cube, that will be kept as it is, and gme is replaced by gre square. This we have proved earlier, and the net equation will be 2 pi under root h plus re whole cube divided by gr square. Now, if we rationalize re square, that is multiply by re and divide by re, then our formula will become 2 pi under root re over g into 1 plus h over re to the power 3 by 2, where h is the height where the satellite is situated. Re stands for the radius of Earth, g is acceleration due to gravity. Wherever we write capital G, that is the gravitational constant, and me stands for the mass of the Earth. So these are the formulas for the time period. We modify by putting some other results. It is evident from the above expression that t square is proportional to r cube, and that is what the statement of the Kepler's third law, which we have discussed in the earlier portion. So it is true for circular motion also, as well as for the elliptical orbits. So for a satellite revolving very close to the surface of Earth, h must be neglected and only radius of Earth to be considered. That is, re is to be considered. So t, time period, is equal to 2 pi under root re over g. Now we put the value of pi, we put the value of g, that is 9.8 meters per second square, and radius of Earth nearly 6,400 kilometers, or we convert it to meters. Then we get our result in seconds, and those seconds are divided by 60, and our value will become 84.4 minutes. Therefore, the minimum time period of satellite revolving very close to the surface of Earth is 84.4 minutes. Now, from expression t is equal to 2 pi under root r cube over gme, we can say that the period of satellite depends upon the orbital radius, and the relation is t square is proportional to r cube. So this statement is known as the Kepler's formula or the Kepler's law. As the radius increases, simultaneously the time period also increases. Now we come towards the energy of satellite. When we use the term energy, we are referring to the potential energy of satellite as well as kinetic energy of satellite. So when we use strictly the energy of satellite, we are referring to total energy of satellite. That is algebraic sum of kinetic energy and potential energy of satellite. Some more thing is to be known about the energy. Potential energy is the work done to bring unit mass from infinity to a point in the gravitational field of the given mass. Whereas when we use the term kinetic energy, it means bodies revolving around the another body, and the force responsible for revolving the body will be the centripetal force. So we have to find potential energy, then we will find kinetic energy, and then we will add both the energies, and that will become total energy of satellite. So when we calculate the total energy of satellite, that is the energy with which this satellite is bound with the center of Earth. So, if we provide energy to the satellite, which is just very close to the binding energy, then the satellite will escape from the gravitational pull of the Earth. This concept, which I have just now spoken, will be used later on. So now, first of all, we come towards the potential energy of satellite. That is the work done. Potential energy means work done to bring the mass from infinity to a point in the field of the another mass. So ME is the mass and it will generate the gravitational field, and small m is brought from infinity, that is outside the field, and m is situated at distance r from me, and g is the gravitational constant. So this formula can be received by using the force of gravity. So we can say that potential energy is basically the work done, and work done is force into distance, where force can be taken as g m over r square, or g m1 m2 over r square multiplied by r. One r will cancel off, and we will get this expression which is indicated, that is potential energy is minus gm em over r. We are using the negative sign because work is done in bringing the mass is against the Earth's gravitational pull. Now we come towards the kinetic energy of satellite, and that is half mv square, where m is the mass of the satellite and v is the orbital velocity. So we have just now derived the function for the orbital velocity. So that function will put here and we square the number, and then we get the kinetic energy. So kinetic energy is half mv square, v is the orbital velocity, and the net expression after putting the value of orbital velocity in half mv square, we will get gme m divided by 2r. Now this is the kinetic energy, and potential energy is minus gme over r. So we add both the energies. When we add both the energies, then we will get a function minus gme m over 2r. So now whatever I have spoken earlier, the same is indicated as total energy of satellite. The total energy of satellite is the algebraic sum of Ke plus Pe, that is kinetic energy and potential energy. So we add minus Gm Em over R into Gm Em over 2R. So this will be the next net expression. Now we can say that total energy of satellite is half of the potential energy of satellite, and that is equal to minus kinetic energy of the satellite. Now we come towards the binding energy of the satellite. Now binding energy is nothing, it is the total energy with which the satellite is bound to the earth. Bound to the earth means it is going on orbiting around the center of the earth, just on the circumference. So the energy with which a satellite is bound to the earth is called the binding energy. If we supply some external energy to the satellite, which is equivalent to the binding energy, we find that satellite will absorb that energy, because energy is neither created nor destroyed. After absorbing, it will just exceed the binding energy of satellite and it will leave the orbit. This situation is called escape. So the satellite escapes from the gravitational pull, and the velocity provided, that is called the escape velocity. And it is found that by calculation, the escape velocity of the satellites from the circumference of Earth is nearly 11.2 kilometers per hour. Now let us have the details of the binding energy of satellite. So binding energy is the energy given to satellite in order that the satellite escape away from its orbit. So binding energy will be equal to minus total energy, that is GMEm over 2R, that is equal to the kinetic energy. If energy is equal to GMEm over 2R is provided to the satellite, it will escape from the gravitational field of the planet. So in that case, that will become the escape velocity. So unless a revolving satellite gets extra energy, it would not leave its orbit if the kinetic energy of satellite happens to increase. Two times the satellite would escape. If the orbital velocity of satellite revolving close to Earth happens to increase to root 2 times, the satellite would escape. That means if orbital velocity increases to 41.4%, the satellite would leave the orbit. Now we can put this whole thing in another words also. That is, if we wanted to calculate the orbital velocity, we say V is the orbital velocity or V naught is the orbital velocity, and that is equal to under root GR. But if it is escape velocity, it should be 2 root GR. Now, total energy of satellite is always negative. When the energy of the satellite is negative, it moves in either a circular or elliptical orbit. So up to the time the energy is negative, it means it is moving in an orbit. Now binding energy is equal to kinetic energy, and kinetic energy is equal to minus total energy, that is equal to minus potential energy divided by 2.